Okay, welcome everybody to the second webinar of the bootcamp that we are doing for Google for Startups Accelerator. Today we have Shayak Paul, who is a machine learning Google developer expert and also a mentor, and would have met a few of you in the last 2 weeks during the diagnostics as well as the mentorship program. And he's going to do a talk on model optimizations 101. And Shahid, I'll leave it on you on how do you want to do the questions, if they have any in between the sessions or after the sessions. It's all over to
Yeah,
you.
both works for me. So as long as folks are coming with questions, I'll be checking the Meet chat in between regular intervals. So if I am able to answer the questions right away, I'll do so. Or otherwise, we can do a full-blown Q&A after the end of the session. Or they can always reach out to me in an emailing capacity. So anything works.
Perfect. Okay, you can start, Shahid.
Yeah. Okay, so are we good to go? Should I start?
Yes. If there are others, they can join in between. It's already
Okay.
11:05, so you don't.
Okay, fair enough. That works for me. Hello everyone. Good morning. My name is Sayak. The Bengali version of that pronunciation is Shayok. Today I am going to be talking about model optimization 101. And before that, let me quickly give a round of intro about myself. Not really bragging about myself here. I work as a deep learning associate at a company called PyMedSearch. We are into the education business. Uh, during my free time, I like to contribute to open source initiatives like TensorFlow Hub. I like to binge watch Netflix stuff and all of my coordinates, all of the stuff that I have written so far, and all of the conferences that I have ever spoken at. All of those things are available at sayak.dev. That's sayak.dev. So I'm going to be quickly turning off my camera and get started. And before I actually get started, I would like to give an overview of the ideal audience that I'm expecting. So this session is going to be useful for all the machine learning engineers out there that are looking for ways to optimize their models for production purposes. So if you guys are into production machine learning systems, and if you are looking for ways to reduce your model sizes, if you are into reducing the latency of your serving model, then I believe this session is going to be helpful for you. And if we could do a quick yes no round as to the question, if you are already using the philosophy of tiny machine learning models in your business applications, then I would really appreciate that. So how many of you are into that tiny machine learning and machine learning optimization business already? Or if you are looking for ways to reduce your model size or and still be able to retain your model performance. So if you could do a quick yes no, that would be great. That would help me set the context. Just yes no would be fine.
Yes, we are looking to build in our business. We are looking to build machine.
Okay, fair enough. I mean, rest can also state their opinions via messages. I would also appreciate that. Okay, so far I have got 2 years, but hopefully after this session, you would want to optimize your machine learning models anyway. So that's my hope. Okay, let's get started. So this is the brief kind of overview of what all we are going to be covering in this session. So I'm gonna start with what is model optimization to keep it very consistent and kind of complete. Why should we really care about it? Different areas for a model to optimize, and this is not going to be anyway extensively comprehensive, because machine learning is a very volatile and ever evolving field. You never know what is an exhaustive list of areas in a model to optimize. So I'm going to be focusing on the most practical ones, and hopefully that's going to be useful for you folks. Of course, we'll be diving deeper into two of the prime model optimization techniques, quantization and pruning. We'll not be discussing knowledge distillation today, but I'll be providing you with resources that will definitely help you to get started with that. And I'll be discussing some of the practical tips. And as I mentioned, we'll be, of course, doing a round of Q&A. And just as I mentioned, if you have any questions at any point in time during the session, feel free to ask away. I'll be checking the chat at regular intervals. So if I can answer that, I'll answer that right away. So, yeah. I also wanted to shed light on the kind of conventions that I'm going to be using. TensorFlow Lite is going to be substituted as TF Lite. TensorFlow Model Optimization Toolkit is going to be substituted as either MOT or TF MOT, and TensorFlow is of course going to be substituted as TF. So yeah, just so that you do not miss out on this fancy abbreviation. Okay, so let's get to it. So what is model optimization? To my understanding, model optimization can really be an umbrella term for reducing model size, speeding up your inference time, and of course preparing your model in such a way that it reduces its power consumption. And all of these three things can play very crucial roles when we are talking in terms of production machine learning systems. So I'll be discussing the rationale behind some of these points in a bit more detail. But if you have any questions at this point, feel free to ask away or we can continue. Okay. So why should we really care about it? So the first and foremost point to me is your world-class and state-of-the-art but heavy machine learning models are likely not suitable for deployment. And yeah, many of you might be using tiny machine learning model architectures in the first place. For example, MobileNet V2 or MobileNet V3 or EfficientNet Lite or MNASNet and SSD MobileNet and stuff like that. And the reality is these models are already optimized for mobile-based deployments. These models are already optimized in terms of latency and its size. But there are many, language models and other image-based models which are still heavy, and their heaviness can always, come up with barriers when we are talking in terms of production machine learning systems. For example, if you were to directly deploy your custom trained BERT model, you would probably want to reduce its size to make it eligible for your production pipeline. So again, if we are talking in the context of TinyML, consider deploying your heavyweight models to Raspberry Pis, mobile phones, microcontrollers. I'm sure you folks are already doing this. So this is a very important consideration to make, that if our target runtime hardware are include Raspberry Pis mobile phones, we cannot probably fit a BERT model or a GPT-3 model inside those tiny devices. At least in an offline capacity. I'm not talking about cloud APIs. Of course, heavier models tend to produce latency. We all saw how much latency the initial version of RCNN model produced. And anyway, BERT is also not fast enough to infer in extremely real-time situations. So it's a no-brainer that heavier models tend to have more latency, because the computation graph is extremely complicated to compute in a very faster manner, and that tends to result into latency, which might not be suitable for mission critical applications, just as I mentioned. Sorry for the font change. I do not know what I did there, but yeah, heavier models can affect your infrastructure cost significantly. Consider serving a 2 GB model as opposed to serving a 2 MB model probably. Of course, the difference in the infrastructure cost that you will incur will be significant, right? The contrast will be significant. And what if cloud-based model hosting is not an option? What if your target runtimes are extremely resource constrained, where network connectivity might be still an issue? What if you need to meet with privacy regulations, where wherein you need to meet with close-knit interactions and stuff like that. So cloud-based solutions are not always the way forward. And now I'd like to discuss some of the different areas for a model to optimize. Again, I would like to, state this disclaimer at the very beginning that it's no way an exhaustive list, but I tried to pick up on the most practical ones. So if you folks have any questions at this point, feel free to ask away. You can use the chat to ask questions. That would be easier for us to track, I guess. Okay, I'll just continue. So reduced numerical precision is probably the first and foremost thing that comes to the mind. Generally, your model's parameters and activations, and by model, I am essentially referring to a neural network here. That's why the segregation between parameters are trainable variables and activations, right? So your model's parameters and activations are generally represented in float 32. So what if we could reduce that numerical precision without having to compensate with your model's accuracy? The second point would be, are all the operations in a model's computation graph needed during inference? Things like dropout are typically not needed while you are making inference with your model. Batch normalization has a very different behavior during prediction time, and things like group normalization or instance normalization or any form of normalization that you typically incorporate inside your model's execution graph, they might have different inference behavior. So it's important to account for that fact and being able to carefully discard all those operations that are typically not used during inference, because that can help you to simplify your model's computation graph to a great extent. For example, oftentimes we tend to fuse a different number of operations, and it's typically known as layer merging or layer fusion and things like that. So yeah. So the third point would be, do all the parameters or trainable variables in your model contribute equally to the model performance? And it would turn out that it doesn't. We'll discuss all of these things in a way more detail in a moment. So another common mistake that I see in most of the GPU based or even CPU based serving infrastructure is this back and forth between GPU and non-GPU kernels. For example, you are probably loading your model's your model file or the entire computation graph, and not all of the operations might be supported on your serving GPU. So in that case, you would first need to pop all of your operations inside your model into a CPU first, and you would then need to filter all the operations that are supported on a GPU. So this, comparable back and forth between GPU and non-GPU kernels can introduce latency to a great extent. And I have also linked to an article that explains this wonderfully. And don't worry, I'm gonna be sharing the slides after this session, and so you can always refer to it when it's needed. Okay, so if I were to map some of these potential optimization areas inside a model to literal techniques, this would go something like this. So reduced numerical precision, we deal with that problem by means of quantization. And as I mentioned, not all the operations of a model graph are needed during inference. So layer fusion, things like layer fusion, constant folding help us deal with that problem. And do all the parameters of a model contribute equally to a model's performance? As we will see, pruning tries to approach this problem, and it does provide us with a very systematic framework to deal with this problem. So yeah, and in this session, we'll be focusing on quantization and pruning mainly. So before we proceed to the next section, if you have any questions, feel free to ask away. I'll just continue. So the first and foremost recipe that I'd like to discuss is quantization. It's probably one of the most practically accepted techniques when we talk about model optimization. And I'm going to be giving you a very simple overview of what quantization means in deep learning. For a more detailed overview, I'll be sure to refer to you with good resources, so that if you are interested, you can always pick up on it if you're interested. So quantization at a very high level works by reducing the precision of the numbers used to represent your model's parameters and sometimes activations too. We will see what's the difference between quantizing your model's parameters and activations separately and all at the same time. There are many differences, and we'll be discussing them shortly. And as I mentioned, in most of the cases, your model's parameters and activations are represented in float 32 numerical precision. So of course, that leaves us with an opportunity to reduce that numerical precision, probably in float 16 and even in integer 8 quantization. We have binary neural networks these days, but in my experience and for what it's worth, for all the practical applications that I have seen so far, integer 8 quantization and float 16 quantization are the most used ones. So PPT you will be provided with, and recording you will be provided with. If I'm not wrong, Manu can correct me. So if you reduce your numerical precision of your model, this results into smaller model sizes and faster computations, because when you reduce the numerical precision of your model in order to represent the activations and parameters, the runtime gets significantly faster. It becomes significantly faster to compute all the activations with reduced precision parameters. So here's a pictorial representation of the ranges that might look after they are quantized. So on the left side, we have a continuous range of parameter values or the weight values, and on the right we have the quantized variance. So we see the continuity in the ranges have been eliminated by means of quantization, and the numbers would now get mapped to some discrete values rather than being on a continuous range. So this helps tremendously in boosting models inference time. So there are mostly two flavors of quantization available. One is known as post-training quantization. It's probably the most common one. And there's also another form of quantization. It's not really quantization, it's kind of fake quantization. It's known as quantization-aware training. So let's start with post-training quantization. It happens after your model is trained, right? And let's just start with a code example. And the code examples are going to be in Keras, but these ideas apply equally to any other domain in deep learning, and you can realize all of these things even if you are using a different framework like PyTorch. So let's start with a very humble data set. Now here we are trying to model the relationship of y equals to 2x minus 1. So here's our humble data set. Here's our humble model with the Keras's sequential API. I'm compiling this model to use the stochastic gradient descent optimizer and to minimize the mean squared error. So here's how you train your model in Keras for 50 bucks. And here's exactly how you would quantize your model in a post-training quantization capacity, right? So in that highlighted code listing, I'm first loading my Keras model with the from_Keras_model function that is provided by the TF Lite converter class. I'm then providing the optimization recipe in which I'd like to quantize my model, and finally I'm calling the convert function on the converter object, and that's it. That's really it. That's just 3 lines of code in order to export a quantized model in TensorFlow and TensorFlow Lite. So there are different optimization recipes available. Here we are using the tf.lite.optimize.default policy, and in most of the cases I've seen this just works right off the bat. And there are other optimization configurations available. If you would like to optimize your model for latency, or you would like to be very specific and you would like to optimize your model for size, you have your options available right there. And serializing this model is just a matter of few keystrokes. So yeah. And there are different forms of post-training quantization available in TF Lite. It depends on the way, it depends on whether or not you would like to quantize your model's trainable variables or your model's parameters, or you would like to also quantize your model's activations along with the model's parameters. And depending on these different recipes and depending on the target runtime that you might be dealing with in your production machine learning system, you are absolutely given the authority to mix and match in between these different quantization recipes and choose the one that works the best for you. So yeah, probably you are using an HTPU in your deployment purposes. So probably going with probably going with the full integer quantization recipe would be the best for you. So yeah, I mean, you get the point, right? If you have a target runtime that's already known to you, and if you are chasing a certain kind of benefits, you can always mix and match in between them, and you can choose whatever works the best for you. Sorry, is there a question? Okay. Okay. So I have also provided a notebook so that you can see.
Sir, one quick question. Like, any impact on performance because of?
I'll be getting to that shortly. In a future slide. Yeah. So I have also provided with a fully worked out example in case if you'd like to refer to a quickly worked out example. So yeah, feel free to check that out. And now let's talk about quantization-aware training a bit. But before that, let's address the problems that that come with quantization, post-training quantization. So when we are acting in a post-training quantization capacity, that can introduce information loss, because we are ultimately reducing our model's numerical precision, and we are kind of snatching away its expressiveness in order to learn discriminative features in order to learn a particular function mapping. So when we are directly introducing that information loss, that might lead to drop in accuracy. And what if an immediate trick that might come to our mind is, what if we could somehow inform the model about this information loss while training it? What if we could make our model aware of this information loss while it is training it? Probably in that way it will be able to deal with the information loss that's coming to it in a later phase of deployment. So that's exactly what quantization-aware training is for. So we'll be discussing this now. So again, we start by in a Keras setting, we would probably start by initializing our models using the sequential API provided by Keras. So it's just one line of code in order to instruct Keras that, hey, you should train your model in a quantization-aware training capacity. So I'm going to be referring to quantization-aware training as QAT. So yeah, just wanted to let you folks know. And the rest of the things exactly look similar. You would compile your model in the same way, you would then fit it, and yeah, boom, voila. And I've also provided a separate notebook that provides you with a fully worked out example of quantization-aware training. So feel free to give that a check. And while we are in the model optimization business, it's really important to make sure that we are exporting very lightweight models, and at the same time we are also being able to retain the original model performance. So Madhur was probably asking about the kind of impacts of model performance. So here's it. Here it is. I'm going to be quickly running you folks through it. So in the first row, we see a regular image classification model, and I forgot to include the size, and it should be around 11 MB. It's a regular, model trained in Keras, and it's able to provide us with a validation accuracy of 88%. And the second model was trained using quantization-aware training. It's again, the size is here 11 MB. I mistakenly, I forgot to replace the size. So typically in this phase, we will not be optimizing our models because we are training it. And the post-training quantization part comes after you are done training your model. And with quantization-aware training, we see an instant boost in the validation accuracy, and we are getting a whopping increase to 92.91. And when we are actually doing the post-training quantization part with the optimization configuration set to the default recipe, we are seeing a steep comparison here, right? So the regular model that was not trained using quantization-aware training, it's not able to retain the original model performance, and we see a decrease of almost 13%. And the model that was trained using quantization-aware training, after getting quantized, is able to retain the original model performance. So I hope you have your answer right there.
Yeah, so just one more question is like, what about the response time of these models?
So if you are talking about inference time, the original models that were, trained using the classical model.fit or even the custom training loop capacity, the inference time will be way higher than the quantized versions of the model. But if you are, if you are drawing comparisons with these two variants, quantized model of the non-QAT one and the QAT one, there's absolutely no difference in the inference time. And to have a more closer look about the inference time, I would encourage you to check out the notebook to have a clearer overview of how the inference time gets affected.
Sure.
Yeah, sure. So, okay, we have the benefit. Yeah, go ahead.
One question. So, is it specific, that quantization model creates better accuracy for a particular domain? Is it, can it happen that for a different domain, let's say we are working, a non-quantized model gives a better accuracy?
So a non-quantized model is supposed to be always giving you with better accuracy because there's no information loss happening inside it. But as you mentioned, it can, vary. It can depend a lot on the kind of model architecture that you are using. So if you are using models that incorporate things like, self-attention or spectral normalization and stuff like that, in those cases, it's not really recommended to quantize the attention layers because that provides very significant amount of information about the data. So you would want to be careful, and you would like to, quantize very specific parts of your model in those cases, and TF Lite APIs provide you with enough capabilities. With if you would like to quantize specific parts of your model or specific layers of your model, that option is available with you with TF Lite APIs.
So yeah, that can happen. That right? Like. For a particular domain or particular set of problem statement, a quantized model is giving a higher loss than to add up in the increasing the accuracy, right?
Yeah, that can happen, but if you are not careful enough, just as I mentioned. So while quantizing your original training model, you would like to incorporate the practices that I just shared. Probably your model has a very important layer that you would not like to quantize. So if you follow those kind of practices, and if you train your model in a quantization-aware way, chances are that your model after getting quantized will be giving you the same kind of performance.
Okay. Thank you.
Sayak, one more question. How does this work in transfer learning?
Sorry?
How does this work in case of transfer learning?
So the result that I'm demonstrating is actually coming from a transfer learned model. So what I did was I took a MobileNet V2 model pre-trained on the ImageNet dataset, and I then took the Flowers dataset and I fine-tuned the MobileNet V2 on the Flowers dataset, and the results that we are seeing here today is coming from that fine-tuned MobileNet V2 model.
Awesome. Thanks.
Yeah, sure. Okay. So the recipe for us has been so far kind of like this. So train a model using quantization-aware training, and just as I mentioned, it's absolutely possible to train parts of your model or specific layers of your model using the quantization-aware training scheme. And I've also linked you to the documentation that shows you how to do this. And then hybrid quantize the model and evaluate. Basically, hybrid quantization recipe refers to the optimization that I was using, tf.lite.optimize.default, and then yeah, enjoy the benefits. So yeah, and if someone was asking me about the training time, and yes, quantization-aware training can take substantially more time than the regular training loops, because in quantization-aware training, the model is trying to figure out what's the best way to compensate for the upcoming loss it's going to incur. And also, when you are training your model in the quantization training aware capacity, many fake quantization nodes get inserted into your original model's computation graph. So so your model's computation graph becomes a bit more complicated, and that's why it takes substantially more time than the regular training loops. So yeah. So these are the kind of stakes that you get with quantization-aware training, and there's a certain post-training quantization-aware recipe that's known as full integer quantization, where your model's activation and parameters, all of them get quantized to integer 8 variant. And with quantization-aware trained models, full integer enforcement might not be possible. And if you are dealing with HTPU-based, deployment runtime, having your model in integer precision is typically a requirement. You cannot bypass that part. So if you are dealing with HTPU-based target runtime, then it's not recommended to use quantization-aware training basically, but it's still a work in progress to mitigate this issue. So keep an eye out on this particular GitHub issue that I have mentioned here. So the third stake is it requires your model to be entirely written in Keras, and it also assumes that you have full access to your model code and training dataset, which might not be possible in many instances. I understand that. So I just wanted to also make sure that you are fully aware of the stakes that come with quantization-aware training. And yeah. So if quantization-aware trained model is failing to produce good performance after post-training quantization, report that phenomenon immediately, and chances are that probably the quantization-aware training API folks might have introduced some bugs mistakenly, and they take care of these things very seriously. So be sure to report any such phenomena if you discover that. Okay. So I have linked to a couple of resources that gives you the sort of best practices, both for quantization-aware training and post-training quantization. And I have found them to be highly useful if you're really serious about TinyML and embedded ML systems. So yeah, feel free to check them out. So if you have any questions at this point, feel free to ask, because we are going to get into a different quantization technique now. Okay, so now we'll be discussing the model optimization technique called pruning. So the basic premise here is, do all the parameters of a model contribute to its performance equally? So yeah, let's start with that premise. So the point here is, low magnitude parameters usually do not contribute to model's performance and can be discarded easily. So typically we initialize our neural networks in a very specific way, and we would want our trainable parameters to be as close to a 0 so that it's able to unravel the underlying function from your data set. So it turns out that when we initialize our weight to be as close to a 0 as possible, there would be some of these weights that would remain in that particular magnitude for the entirety of your training. And it only means that those weights are probably not important enough for your model to optimize during the training procedure in the first place. So those low magnitude parameters are typically referred to as not so important for the optimization task, and the rationale here is they might not even contribute to your model's performance in the first place, and they can be easily discarded. And when I say discard, I essentially mean zeroing those parameters out. And this particular recipe is commonly referred to as model pruning. And model pruning can take place while and after training, as you would see. So switching gears to your model's parameters. So here's an example of a shallow, fully connected network. And here's how it might look like after its parameters are kind of pruned. You see, I have eliminated all the unwanted connections from in between the nodes. So yeah. And let's take a quick code example. Same drill. You would probably construct your model using the sequential keras API. You would then compile it and fit it. And yeah, with just 3 lines of code, you would prune all the low magnitude parameters. You would then compile your prune model, and you would then again train your prune model in order to be able to retain the same performance as the original model. So that's a very neat little trick, but it works tremendously fine. So get onboarded with pruning. It's really these 3 lines of code, and I would highly encourage you folks to try this out if you're interested. So at this point in time, you are probably wondering, this whole pruning thing, discarding connections between nodes inside a neural network, isn't this similar to dropout? Yeah. So yeah, if you have any pointers to assert here, now is your time. So the question is, isn't pruning similar to dropout? If not, what are the differences? I'll give you 30 seconds. So it turns out that pruning is actually different from dropout. So although dropout is a training time technique, it kind of drops connections to nodes at random during training. But during evaluation or during serving, dropout is not typically used. Keras has different ways to compensate for the dropout factor, but the dropout rate or the entire philosophy of dropout is not typically used during evaluation. While pruning is both a training time and serving time technique. So there's a significant difference in between dropout and pruning if you were confused. So something to ponder upon. A pruned version of a heavy network is yielding almost the same kind of performance as you would see in the onboarding notebook that I just linked earlier. So it's safe to say that the initial network that we are starting off with is indeed over parameterized with respect to the given data. So after all this time, we are over parameterizing our neural network in order to optimize for a certain training objective. And it's absolutely possible to reduce the over parameterization inside your neural network by means of pruning and still being able to retain to the original model performance. So yeah. And go ahead.
Yeah, Sayak. So Sayak, does pruning also affect the size of the model?
Yeah, absolutely. So when your models become very sparse, so with pruning, you would introduce lots of zeros inside your model. So your model becomes sparse, your model kernels become sparse, and sparse kernels are very easy to compress. So when you would compress a sparse kernel, it typically reduces your model's overall size to a great extent.
Yeah, so I was asking this was because we are essentially introducing zeros in the weights, right?
Yeah.
But my confusion was it only improving the latency time or the weights, the size of the model as well?
Yeah, so it actually optimizes the both. It also it also enhances your inference time at the same time reducing your model size. because pruning can, communicate seamlessly well with post-training quantization recipes that I just showed to you folks.
Okay.
Yeah,
Thanks.
cool.
Awesome.
Yeah, sure. So the folks that are really interested in pursuing the field of pruning, I definitely recommend checking out this talk by Jonathan Frankel, the lottery ticket hypothesis author, the first author of the lottery ticket hypothesis paper, which actually gave us a very systematic way to prune our neural network. So I definitely encourage you folks to check this out if you're interested in knowing more about pruning in general. Okay, so definitely if you are interested in the coding side of things, definitely check this guide out. It enlists where and where not to use pruning. Just as I was mentioning earlier, if your model contains important layers like spectral normalization or attention or even visual attention inside your image-based models and stuff, it's not typically recommended to quantize or even prune those layers because it contains very useful information and stuff like that. So here's another recipe for you. Here's another model optimization recipe for you. Probably you are just interested in making inference with a pre-trained model. So load your pre-trained model, and one can also train their models using pruning callbacks, just as you see in the provided link. And you can also prune certain parts of your model, if not the entire model. Prune your model with respect to a given sparsity, probably 0.7 or 0.8, the target sparsity that you would want to attain for your model. Then retrain your prune model in order to recover the lost accuracy. Because when you prune your model, chances are that your accuracy might get lost. So you'd want to retrain your prune model again to be able to recover that lost accuracy. And just as I was mentioning, quantize your model using the post-training quantization recipes that I just presented. And if you are able to get your expected performance, again, enjoy that or else repeat the steps. So in the coming days, if you're using TensorFlow Lite and TensorFlow Model Optimization Toolkit to try out this optimization recipe, inference will be way more faster if you're using prune models. I mean, better support for sparse networks will be introduced in the coming future. So it's safe enough to say that we can see this release coming in October. So yeah. And yeah, make your own optimization recipes and experiment. Without experiment, you'll never be able to appreciate the potential benefits of this optimization recipe. So I have linked to a bunch of very useful resources in case if you're interested to pursue more on this. And there are different model optimization techniques. Just as I mentioned before, it's no way an exhaustive kind of list. So there are many other model optimization techniques that you might want to discover further or might want to pursue further even. So first one would be movement pruning. So the folks that are very interested in incorporating pruning in transfer learning regimes, movement pruning is your guide. So it was introduced by the folks at Hugging Face. So definitely check it out if you are interested in incorporating pruning in normal transfer learning regimes. And lottery ticket hypothesis is just a mind-blowing paper. If you're interested in pruning in general, definitely check out lottery ticket hypothesis. And I have also mentioned a bunch of other model optimization recipes like knowledge distillation, deep compression, low rank approximation. But in practice, pruning, quantization, and knowledge distillation probably are the most common techniques that you will see. And the deck is available. I'll also share the link in the chat so that you folks have access to it. Let me type it out real quick. And yeah, so this is the link to the deck. And thanks for listening. If you have any questions, we can take them. We have time, it seems.
Thank you, Shayak. If you have any questions, folks, please go ahead and ask. It looks like we don't have any questions.
Okay. Sure.
No problem. Thanks, Shai. Thanks for your time.
Yeah.
Folks, so this
Yeah,
deck and this recording, both of this will be available on the hub. And Shai, I'll also send you a copy of the recording as well as the deck.
Yeah, that would be
In your-
very helpful. Thanks.
Just recording.
And yeah, if you folks are interested to catch me up with any model optimization stuff, feel free to reach out to me via Twitter, or I'll just leave you with my email so that you can contact me.
Shayak is also mentoring. So in case if you want to meet Shayak one-to-one, that can also be done.
Yeah, Manav will be happy to set up the.
Yeah, Manu. Actually, unfortunately, Gaurav was not there on the call today, and Gaurav is a software engineer and handling tech. So it was although we listen entire thing, but it was quite technical for us, me and Sujata. So we'll ask Gaurav to connect directly with the Sayak, and we'll see.
Yeah, Sunil, probably a good idea would be for Gaurav would be to first quickly go through the deck that I presented, and then absolutely feel free to connect him to me.
Yeah, that's why I asked about the recording and this deck, so that I will share it with, and he can directly ask the queries.
Fair enough. That works for me.
Yeah, thank you. Thank you so much for presenting it.
Okay, thank you. Thank you so much.
Okay, thank you.
Yep.
Have a good day.
Bye.
Bye.
Thanks, Shaya.